Welcome to this video. I am Dr. K. Usha, Assistant Professor, Department of Statistics, Sri Sharada College for Women, Salem. So in this video, I am going to talk about unbiasedness. So this unbiasedness comes under the concept of theory of estimation. So before going to that concept, we will see the some basic concept of theory of estimation. So first one is the population, second one sample, third one estimate, then fourth one estimator. So first population. A population is the set of all possible measurements and data corresponding to the entire collection of units. So here population, each and everyone included to study that is called population. We can study the entire population, each and everyone included in the population. That is the population. For example, in the college there are 1,000 students are studying. So that 1,000 students is called the population. Next one, sample. A small group taken from the population, it represents entire population. So first we see the about population. From the population, we can we can take a small portion of the population. That portion represents the entire population. That is called a sample. For example, so already I told in the college there are 1,000 students are studying. From the 1,000 students, I am randomly selected 400 students. That is called sample. So then next one, estimate and estimator. So estimate means the value that obtained from a sample. Then estimator means an estimator is used to estimate a population parameter. So for example, x bar and s square is the estimator, mu and sigma square is the estimate. Here x bar is the sample mean and s square is the sample variance. Then mu is the population mean and sigma square is the population variance. From the estimator, we can estimate the population parameters. So that is the estimate and estimator. So we can see the another example. So I have take a sample of 5 numbers. From the sample of 5 numbers, I would like to take average. So the estimator is taking the average of the sample. Then from finding that value, average value, suppose if I have taken 5 numbers, from the 5 numbers average is 4 now. That 4 is the estimate. The process of average is the estimator. So this is the estimate and estimator. So next we will see the theory of estimation definition. So draw a conclusion about the population from the sample. So already we have studied population and sample. So from the population we have taken the sample. From the sample we can draw the conclusion. So that conclusion gives some inferences. That inference represent the entire population. That is the theory of estimation. So this theory of estimation further divided into two types. One is point estimation and another one is interval estimation. We will see one by one. So first one is point estimation. So point estimation means, so in the word itself we have the point, which means point means particular value or single value. So here we are studying a single value or particular value computed from the sample information, which is used to estimate population parameter. That is the point estimation. For example, a sample mean is a point estimate of a population mean. So we can say that another example. So already we have seen that the college there are 1,000 students are studying. From the 1,000 students, I want to take average height of the students. So instead of I'm taking 1,000 students, I'm taking sample from the population. Out of 1,000, I'm taking 400 students. From the 400 students, I am taking average height. So that height represents the entire population. So that value is that average sample average height is the single value or particular value. So this is called the point estimation. So next one, interval estimation. An interval estimate gives a range of values where the parameter is expected to lie. So we already know about point estimation. Point estimation means particular value or single value. It represents that value represents the discrete data. Here the interval estimation we are using continuous data. So continuous data means we know about 10 to 20, 20 to 30. Between 10 to 20, there is the interval that is called the interval. So, for example, average salary of data scientists in India per annum 2 lakhs to 3 lakhs. That is the interval. From the interval 2 lakhs to 3 lakhs, they get 2.5 lakhs per month or 2.9 lakhs per month, or exactly they get 3 lakhs also. But in the interval estimation, we are studying the interval 2 lakhs to 3 lakhs, like that. So this is called interval estimation. So in this paper, we are mainly going to concentrate about point estimation. From that, we are seeing about unbiasedness. So let's see the characteristics of good estimator. So already we have seen about what is meant by estimate and estimator. So next is the characteristics of good estimator. It will come under the point estimation. The first one is unbiasedness, second one consistency, third one efficiency, then fourth one sufficiency. Let's see one by one. First one is unbiasedness. So biasness means there is no bias. That is called unbiased or unbiasedness. The expected value of the estimate is equal to the population parameter, which means we have the one population parameter mean value mu. Then we can from the population we can take sample. From the sample we can find the sample mean x bar. So both the parameter is equal, which means x bar equal to mu, that is the unbiasedness. So next one, consistency. Here as n is the small n is the sample size, approaches capital N, which is population size, estimator converges to the population parameter. This is called consistency. So here we are taking the sample from the population. This sample size approaches to the population size, which means nearer to the population size. So we'll say that if it converges, now that is called consistency. Then next one, the consistency possesses two conditions. First one is it should be unbiasedness, which means expectation of Tn equal to comma of theta, which means sample mean equal to population mean, like that. Then next one is variance of Tn equal to 0, which means here this n value tends to infinity. Now variance of Tn becomes 0. So if satisfy the two conditions, now that is called consistency. Then next one, efficiency. The most efficient estimator among a group of unbiased estimator, which one is the smallest variance, is called the efficiency. The most efficient estimator among a group of unbiased estimator. For example, I can take an estimator 1, estimator 2, estimator 3 and estimator 4. I have 4 estimator. From the 4 estimator should be unbiased estimator. From the 4 estimator, we are finding the variance. Among the 4 estimators variance. So which one is smaller? That one is the efficiency. So this is the efficiency. The next one, sufficiency. An estimator is said to be sufficient for a parameter if it contains all the information in the sample regarding the parameter. When we say that given parameter is sufficiency, it should be satisfy all the conditions. Then we say that given estimator is in sufficiency. So these all are the criteria of good index, criteria of good estimator. So next we will see the our main concept of unbiasedness. So unbiasedness means there is no bias in the estimator. So first we will see the proper definition of unbiasedness. An estimator Tn equal to T of x1, x2, etc. xn is said to be an unbiased estimator of comma of theta if expectation of Tn equal to comma of theta for all theta belongs to whole parameter space. So here Tn is the one estimator. This estimator is taken from some random sample observation. Here the random sample observation is x1, x2, etc. xn is a random sample observation. Then gamma of theta is the population. So from the population we are taking sample. From the sample we are finding the expectation of Tn, which should be equal to the population parameter gamma of theta. So this is called the unbiasedness. So let's see the example for this unbiasedness. So first example, x1, x2 etc. Xn is a random sample from a normal population. Normal mu comma 1 show that t equal to 1 by n, sum of I ranges from 1 to n xi square is an unbiased estimator of mu squared plus 1. So what they given in the example, we need to find about the given t equal to 1 by n, sum of I ranges from 1 to n xi square is equal to mu square plus 1, which means it is an unbiased estimator. We have to prove that given problem is unbiased or not. So first see the solution. So in this problem, the x1, x2, etc. xn is a random sample taken from the normal population with mean mu and variance 1. So we take that expectation of xi equal to mu, which means mean, then variance of xi equal to 1. This already given in the problem. Given in the problem, normal mu comma 1 mu comma 1 for all I equal to 1 to n. So next now expectation. So we all know about the variation formula. So what is the variation formula? Variation of x equal to expectation of x square minus expectation of x the whole square. So that is the formula for variance. So using that formula, we can from the formula we are taking expectation of xi square right side, then left side, then right side we are writing variance of xi plus expectation of xi the whole square. So already we have values for this variable. Variance of xi value is 1. Then expectation of xi square means we have expectation of xi equal to mu. So 1 plus mu the mu square. So we got this this 1 plus mu square for expectation of xi square. Next we will find the expectation for this estimator. Expectation of t equal to expectation of 1 by n into sum of I ranges from 1 to n into xi square. So now we are taking out the constant 1 by n, then sum of I ranges from 1 to n, then multiplying x into xi squared. So taking expectation for xi square. So expectation of xi square we already find out that value is 1 plus mu square. So next step, this is equal to 1 by n, sum of I ranges from 1 to n, 1 plus mu square. So here we know that value expectation of x square value is 1 plus mu square. So now we know that 1 by n, they given 1 by n, 1 by n, then we can take 1 plus mu square for sum. Now we will get n into 1 plus mu square. So here n and n, the numerator and the denominator n will be cancelled. We will get 1 plus mu square. So we proved that the given problem is an unbiased estimator of mu square plus 1. So that is why we are given, hence C is an unbiased estimator of 1 plus mu square. So this is the example for unbiasedness. So next we will see about another example. Here we are taking three random variables x1, x2 and x3 is a random sample of size 3 from a population with mean value mu. T1, T2, T3 are the estimators used to estimate mean value mu, where T1 equal to x1 plus x2 minus x3 and T2 equal to 2 into x1 plus 3 into x3 minus 4x2 and T3 equal to x1 plus x2 divided by 2 plus x3 are T1 and T2 and T3 are unbiased estimators or not. So in this problem we are going to check whether the estimators T1, T2 and T3 unbiased or not. So first see the problem. So they given random sample of size 3 values x1, x2 and x3. We can take from the normal population with mean value mu. So from that mean value we can find this estimator T1, T2 and T3. So let's see the solution. So x1, x2, x3 is a random sample of size 3 from a population with mean value mu, that is expectation of xi equal to mu. Then next one. So first we will take the T1. T1 equal to x1 plus x2 minus x3. Now we are taking expectation on both sides. Expectation of T1 equal to expectation of x1 plus expectation of x2 minus expectation of 3, which is equal to mu. How? Here expectation of x1 plus expectation of x2 and minus expectation of x3 we are taking for the three samples we are taking x1, x2, x3 as a mu. So here is 1 mu plus here is 1 mu. So 2 mu minus mu. So 2 mu minus mu will get mu. So given estimator T1 is an unbiased estimator of mu. So next one, um, second estimator T2 equal to 2 into x1 plus 3 into x3 minus 4 into x2. So same, we are taking expectation on both sides. So expectation of 2x1 plus expectation of 3x3 minus expectation of 4x square. Next step, we are taking the constant terms outside. So 2 into expectation of x1 plus 3 into expectation of x3 minus 4 into expectation of x square. So here we already know that expectation of x1, x2 and x3 values are mu. So we are substituting in the place of x1, x2, x3 mu value. So what we will get? 2 into mu1 plus 3 into mu1, 3 into mu minus 4 into mu. So totally so 2 mu plus 3 mu 5 mu minus 4 mu. So we will get mu. So T2 is also a unbiased estimator of mu. Okay. So T1 and T2 are unbiased estimator of u. We have proved. So next we will see the estimator T3. So T3 equal to x1 plus x2 divided by 2 plus x3. So now taking expectation on both sides, expectation of T3 equals to expectation of x1 plus x2 divided by 2 plus expectation of x3. So now I'm taking constant terms outside. So 1 by 2 into expectation of x1 plus x2 plus expectation of x3. So from this 1 by 2 into already we know about that x1, x2 and x3 value is the mu. So 1 by 2 into mu plus mu plus mu. Here what will we get? 2 mu divided by 2 plus mu. So what will happen? 2 and 2 will be cancelled. Then mu, there is a mu term plus mu. So what we will get now? 2 mu. So from this T3 estimator, what we will get? 2 mu. But when we said the given estimator is unbiased estimator, which is equal to mu. So given T3 is a not unbiased estimator of mu because we got the instead of mu value we get the result 2 mu. So this is the example for the unbiasedness. So actually I'm referring the books of S.C. Gupta and V.K. Kapoor 2007 Fundamentals of Mathematical Statistics. Those who are interested to learn about the theory of estimation, one can refer that book. They given each and everything in detail. So, so you can refer this book for, you can study further. I am taking in this video unbiasedness only. You can refer that consistency, efficiency and sufficiency. They given all the examples and definition clearly. So if you interested to learn about theory of estimation, you can refer that book. Thank you for watching this video. Thank you.